At 5:16 in the evening on November 9th, 1965, a protection relay at the Sir Adam Beck Hydroelectric Power Station, number 2, near Niagara Falls on the Ontario side of the river, did exactly what it had been programmed to do. The problem was that it had been programmed wrong. A protection relay is a sentinel. Its job is to watch the electrical conditions on the lines it monitors, and if those conditions exceed a set threshold, disconnect the line before damage can spread. Think of it as a circuit breaker scaled up to industrial voltage, governed by a set of parameters an engineer enters by hand. When those parameters are correct, the relay is one of the things that keeps a grid stable. When they are wrong, the relay becomes a fuse set to blow at the wrong moment. On a cold November Tuesday, with the afternoon commute underway and furnaces firing across New York, New England, and Ontario, the northeastern grid was running at near its peak capacity for that time of year. Transmission lines were heavy with load. The margins between what the system could carry and what it was carrying were thin. At 5:16 p.m., the relay tripped. It disconnected one of the 230 kilovolt lines feeding power south from the Beck station into Ontario. The line it cut had been carrying a significant share of the station's output. That power did not disappear. It had to go somewhere. Physics does not negotiate. In the fraction of a second after the trip, the load that had been moving south shifted laterally, transferring onto the neighboring lines in the same corridor. Those lines, already near their limits, were suddenly asked to carry more than they had been designed to handle. Their own protection relays detected the overload and did what they had been programmed to do. They tripped. Now the Beck station had lost all of its southbound lines. It had nowhere to send its power. Generation without a load is a crisis inside the machine. Voltage and frequency begin to deviate from the narrow band that keeps equipment safe. The station's generators shut down automatically to protect themselves. The 1,500 megawatts that Beck had been injecting into the northeastern grid vanished in an instant. The grid, which had been balanced on the edge of its capacity, was now 1,500 megawatts short. Neighboring systems tried to compensate. Lines that had been carrying their normal loads were suddenly tasked with covering the gap. They overloaded. Their relays tripped. Their generation went offline or isolated. The cascade moved east, then south, then in every direction at once. Each protective trip that was meant to contain the damage instead transferred the problem to the next component in line. Station after station islanded itself to prevent equipment destruction. The grid fractured into isolated pieces, each unable to sustain its own balance between generation and load. In 5 minutes, it was over. Approximately 30 million people across New York, New England, and parts of Ontario found themselves in the dark. New York City, in the early hours of what would become a 13-hour outage, was a skyline with no lights. Commuters were stuck in subway cars between stations. Hospitals ran on backup generators. The city that had been illuminated continuously since Thomas Edison's Pearl Street Station in 1882 was, for one night, simply dark. The investigation that followed was thorough. Engineers traced the cascade step by step, identified the misprogrammed relay, and documented how the failure had propagated. They understood the mechanism. What they understood less clearly, and what took years of subsequent analysis to fully absorb, was what the failure revealed about the system as a whole. The Beck relay had not caused the blackout by itself. It had revealed something already present, a grid operating near its limits, with thin margins and a cascade logic that, once triggered, was nearly impossible to stop. The relay was the match. The conditions were the fuel. What is worth sitting with is this: the transmission architecture that was operating that night. The three synchronous interconnections, the routing of high voltage lines, the fundamental design logic of large centralized plants delivering power in one direction to passive consumers, was built during the post-war decades of the 1940s, 1950s, and 1960s. It was built for a specific America, with a specific population consuming electricity at a specific rate. The geographic footprint of those interconnections has not fundamentally changed since the 1960s. The system has been expanded, upgraded, and patched across 6 decades. New plants have been added. Reliability standards have been written and enforced. But the bones of the thing, the skeleton of transmission corridors and interconnection boundaries that determines how power moves across the country, is the same skeleton that fractured on a cold November evening in 1965. That skeleton is now carrying nearly 3 times the electricity it was carrying when it was built. The engineers who built the American power grid were not guessing. They were solving a specific problem for a specific moment with the tools and assumptions that moment gave them. The problem was straightforward. A post-war economy was electrifying at a pace that had no historical precedent. Factories were running 3 shifts. Suburbs were spreading across farmland in every direction. Appliances, refrigerators, washing machines, televisions, window air conditioners were moving from luxury to expectation inside a single decade. The demand for electricity was not a trend. It was a physical fact of the way American life was reorganizing itself, and the utilities responsible for delivering that electricity were scrambling to keep up. What they built in the 2 decades following World War II was enormous. Between 1950 and 1963, utilities constructed nearly 80,000 miles of transmission lines. To put that number in physical terms, if you laid those lines end to end, they would circle the Earth more than 3 times. That construction happened in 13 years, driven by regulated monopoly utilities that had a guaranteed customer base, a guaranteed rate of return, and every incentive to build as large and as efficiently as possible. The economics rewarded scale. Bigger plants produced cheaper electricity. Longer transmission lines reached more customers. Each investment justified the next. The plants themselves were growing at a rate that would have seemed implausible a generation earlier. In 1950, the largest steam turbine in commercial operation generated about 208 megawatts. By 1965, that ceiling had risen to 1,000 megawatts. A single plant could now power a city. Engineers referred to this as the era of limitless economies of scale, and for a time, the phrase was not hyperbole. Thermal efficiency more than doubled between the late 1930s and the mid-1960s. The price of electricity, measured in real dollars, fell by nearly 60% between 1945 and 1965. Every year, the same dollar bought more kilowatt hours than it had the year before. The system that emerged from this build-out had a coherent logic. Large generating stations, coal, oil, the first nuclear plants, sat at the top of the hierarchy, producing power at high voltages. Transmission lines, strung between steel towers across hundreds of miles, carried that power to regional substations. Substations stepped the voltage down for local distribution. Homes and businesses received electricity at the end of this chain, drawing what they needed and sending nothing back. The flow was always in the same direction: generation to transmission to distribution to consumer. One way, every time. By the 1950s, 3 major synchronous interconnections had taken shape. The Eastern Interconnection covered roughly 2/3 of the country, from the Atlantic coast to the Great Plains. The Western Interconnection covered the remaining western states. Texas maintained its own separate grid, the result of regulatory and political history that kept it largely isolated from its neighbors. These 3 systems tied together what had previously been a patchwork of isolated regional utilities, allowing power to flow across state lines and enabling utilities to share reserve capacity. A plant in Ohio could, in principle, help cover a shortfall in Pennsylvania. A dam in the Columbia River Basin could support California's peak demand. The engineers who designed this system were building for the America they could see. In 1960, the US population was 179 million people. Per capita electricity consumption was a fraction of what it is today. Residential customers used electricity for lighting for a handful of appliances and for the occasional window unit on a hot summer afternoon. Commercial buildings were lit and cooled, but the loads were modest by current standards. Industry was the heavy consumer, but industrial loads were predictable. This ran during business hours, at known locations, drawing known quantities of power. None of this required the grid to be flexible. Flexibility was not a design priority because the system had never needed it. Power flowed from where it was generated to where it was consumed, at volumes that could be forecast months in advance with reasonable accuracy. The utility engineers who planned that flow were not wrong to build for those conditions. They were building for the world they had. The 3 interconnections those engineers established, the boundaries they drew, the corridors they chose for high voltage transmission, the logic of the network topology, have not fundamentally changed since the 1960s. This is not widely understood. The public conversation about the grid tends to focus on what has been added: new plants, renewable energy, smart meters, digital controls. Those additions are real, but the underlying skeleton of the system, the high voltage transmission corridors that determine how bulk power moves across long distances, follows routes and respects boundaries that were set down when a steam turbine the size of a small building was the cutting edge of engineering, and a residential electricity bill covered a refrigerator, a few lights, and not much else. That skeleton was not designed to be neutral about the direction of power flow. It was designed around the assumption that power always moves one way, down from large central plants toward dispersed consumers. It was not designed for a world in which millions of rooftop solar panels push power back up into the distribution system, or in which a single data center in a rural county draws more electricity than the entire small city nearby, or in which the peak demand on a hot July afternoon is shaped less by residential air conditioning than by the cooling systems of server racks running artificial intelligence workloads around the clock. The engineers of the post-war decades built something that worked brilliantly for the world they were given. What they could not do, what no engineer can do, is build for a world 60 years away that would use their infrastructure to carry a load 3 times the size of anything they modeled, through equipment that would long since have passed the midpoint of its design life. They built what was needed. The question the grid is now living with is whether what was needed then is sufficient for what is being asked of it now. After the lights came back on in November 1965, the people responsible for the American grid understood they had a problem that could not be ignored. 30 million people had lost power because a single relay at a single station had been set incorrectly. The cascade that followed was not a freak event, not an act of nature, not the result of some exotic failure mode that no one could have anticipated. It was the result of the grid operating exactly as designed, with protective equipment doing exactly what it had been told to do, and the outcome was still catastrophic. The system had no margin for error, and when the error came, there was nothing to catch it. The response was institutional. In 1968, 3 years after the blackout, the electric power industry created the National Electric Reliability Council, the organization that would eventually become the North American Electric Reliability Corporation, known today as NERC. Its founding purpose was specific: establish reliability standards across the entire transmission system so that all utilities in all regions were using the same engineering principles and the same safeguards. The patchwork of regional practices that had allowed one misprogrammed relay in Ontario to darken New York City would be replaced by a coordinated framework with teeth. The centerpiece of that framework was a concept engineers call N1 contingency planning. The name is a shorthand for a straightforward requirement. At any given moment, the grid must be capable of losing any single component without that loss causing a cascade. One line trips, one transformer fails, one generator goes offline. The system absorbs the loss and continues operating. That is the standard. Think of it this way. A bridge engineered to N-1 standards is not just designed to carry the weight of the traffic currently crossing it. It is designed to carry that weight even if one of its main support cables snaps without warning. The remaining structure must hold. The bridge must not fall. The cable can be repaired later, but nothing collapses in the meantime. Applied to the grid, N-1 means that transmission planners model every component in their system and simulate its failure. They remove a line from the model and ask, do any remaining lines overload? They remove a transformer and ask, does voltage collapse in the region it was serving? They remove a generator and ask, does frequency stability hold across the interconnection? If the answer to any of those questions is yes, the planners are required to fix the problem before it becomes real, either by adding capacity, rerouting flows, or installing a new equipment. It is a serious and disciplined standard. The decades of grid operation between NERC's founding and the early 2000s were, by most measures, substantially more reliable than what came before. The framework worked for what it was designed to do. What it was designed to do, however, was ensure the stability of the grid as it existed in the late 1960s and 1970s. A grid of large centralized plants, passive consumers, predictable loads, and one-way power flows. A grid whose demand could be modeled with reasonable confidence months in advance, because the consumers at the end of the line were running appliances and factory equipment whose behavior was well understood. A grid where the single greatest risk was a component failure during a period of peak but foreseeable demand. N-1 does not require the system to survive two simultaneous failures. It does not require the system to survive a component failure during conditions that fall outside its historical design envelope, such as temperatures 40 degrees below what the equipment was built to handle. It does not account for the physics of a grid where power flows in multiple directions at once, pushed and pulled by millions of distributed solar installations whose output varies with cloud cover and time of day. It does not model the behavior of a single large new consumer, a hyperscale data center drawing a gigawatt of power around the clock, connecting to a regional grid that was not designed to concentrate that much load in one place. The standard was written for a system. The system has changed. The second period of grid development, running roughly from 1965 through the early 2000s, was focused primarily on reliability upgrades and regulatory reorganization, not on expanding the grid's fundamental capacity. NERC set standards. Regional entities formed to enforce them. The 1970s oil crises added pressure on energy policy and accelerated investment in nuclear and coal. But the basic architecture, the transmission corridors, the interconnection boundaries, the centralized plant logic continued largely unchanged. The work of those decades was making the existing system more reliable. It was not rebuilding it for a different future. That distinction matters because of where it left the system by the time demand began accelerating again. A grid that spent 35 years improving its reliability within an existing design envelope did not emerge from those decades better equipped to handle a tripling of load or the bidirectional power flows that come with distributed generation or the unpredictable demand spikes of a data center economy. It emerged more stable within the conditions it had been built for. The conditions, however, did not stay stable. The N1 standard remains in force. NERC continues to set and enforce reliability requirements. The investment in grid reliability between 1968 and today is real and consequential. None of that is in dispute. What is in dispute, or at least in active tension, is whether a reliability framework designed for one version of the grid is sufficient for a version that carries 3 times the load through equipment that has passed the midpoint of its design life into a demand environment that the original engineers could not have modeled because the loads driving it did not yet exist. The framework called the relay problem. What it was not built to catch is what comes next. Somewhere in the transmission corridor near your city, there is a steel lattice tower that was erected during the Johnson administration. It has been standing in the same field, or the same right-of-way, or the same stretch of mountainside for somewhere between 50 and 60 years. It has been through ice storms and heat waves, through the mechanical fatigue of wind loading that cycles through the metal 10,000 times a year, through the slow oxidation that works on steel regardless of how well it was originally galvanized. The conductor it holds, the aluminum cable carrying high voltage current across the span, has been thermally cycled through decades of summer peaks and winter lows, each cycle expanding and contracting the metal in ways that accumulate over time. The insulators connecting that conductor to the tower are ceramic or glass, materials that degrade under ultraviolet exposure and atmospheric contamination at rates that vary by region and that accelerate in industrial corridors. That tower is not an anomaly, it is the median. According to the American Society of Civil Engineers 2025 Infrastructure Report Card, drawing on U.S. Department of Energy data, 70% of the nation's transmission lines are 25 years or older. 70% of large power transformers are 25 years or older. 60% of circuit breakers are 30 years or older. A 2024 DOE study found that 55% of distribution transformers, roughly 40 million individual units, are more than 33 years old. The expected service life of a distribution transformer is around 40 years. Read those numbers again slowly, because what they describe is not a system approaching the end of its design life in some abstract future sense. They describe a system that is, right now, operating at or past the midpoint of the life cycle its designers assumed. Transmission lines were built to last between 50 and 80 years. A line installed in 1965 hit the low end of that range a decade ago. A line installed in 1975 is entering the back half of its expected life. The system is not uniformly old, but the distribution of ages skews heavily toward the end of the envelope, and the consequences of that skew are not evenly distributed either. This is where the failure math becomes important, and where most discussions of grid aging stop short of the most relevant finding. Age does not degrade infrastructure in a straight line. A transmission line or transformer that has been in service for 30 years is not simply older than one that has been in service for 20 years in the way that a person is older. The relationship between age and failure probability is not linear. It is a curve, and the curve bends sharply upward as equipment crosses into the back portion of its design life. Researchers at the National Renewable Energy Laboratory have found that the rate of transformer failures will accelerate significantly after 2030 as the majority of the national fleet crosses further beyond its expected service life. Think of it this way. Driving a car past 200,000 miles is not inherently dangerous. Plenty of cars reach that number and keep running. But every mile past 200,000 is a coin flip that gets a little less favorable. The car that has been reliable for a decade can shift from functional to critical without much warning, especially if it is being driven harder than it was designed for. The difference is that when a car fails, one person is stranded on the side of the road. When a large power transformer fails in a high-load corridor, the consequences propagate outward in ways that are much harder to contain. This is what the ASCE grade reflects, and the grade itself deserves attention. In March 2025, ASCE released its infrastructure report card, the assessment it produces every 4 years across 18 categories of American infrastructure. The energy sector received a D+. That is a decline from the C- it received in 2021. By ASCE's own definition, a D rating means infrastructure is in fair to poor condition and mostly below standard, with many elements approaching the end of their service life. It is not a failing grade in the technical sense. It is something arguably more concerning. A grade that describes a system still functioning, but functioning in a condition that is deteriorating faster than it is being repaired, with growing numbers of components moving toward the end of the range within which reliable operation can be expected. The energy sector was one of only two categories to receive a lower grade in 2025 than in 2021. This happened while federal infrastructure investment was at historically high levels. The Infrastructure Investment and Jobs Act committed $73 billion to energy. Investor-owned utilities increased transmission spending from roughly $20 billion in 2020 to $27.7 billion in 2023. Record investment, and the grade still went down. ASCE cited three reasons: growing capacity, constraints, rising demand from electrification and data centers, and the lagging pace of transmission and grid modernization relative to the complexity of what the system is now being asked to do. That last phrase is worth holding. Relative to the complexity of what the system is now being asked to do. The grade did not drop because investment stopped. It dropped because the gap between what the system needs and what is being provided continued to widen even as the checks got larger. There is a physical way to understand what a D+ means at the scale of the national grid. A circuit breaker that is 30 years old and operating at the edge of its rated capacity on a 100-degree afternoon is not a broken piece of equipment. It is a functioning piece of equipment with diminished margins and an accelerating failure probability. There are hundreds of thousands of those pieces of equipment distributed across the system. Most of them will continue to function tomorrow and next week and next month. Some will not. The question the age data raises is not whether any individual component will fail. It is what happens to the system when the number of components in the accelerating failure portion of their age curve is simultaneously rising, and the demand being placed on each of those components is simultaneously rising as well. That question does not have a comfortable answer inside a D+ grade. It has a timeline. What had 38 years of reliability standards actually changed? The answer, as of the afternoon of August 14th, 2003, was enough to matter and not enough to prevent what was coming. NERC existed. The N1 standard was in force. Utilities across the country had spent 3.5 decades modeling component failures, building in redundancy, and operating with the explicit requirement that no single loss could be allowed to cascade. The framework that came out of the 1965 investigation was real, was serious, and had measurably improved grid stability across the intervening years. The blackouts that did occur between 1965 and 2003 were smaller, more contained, more regional. The system had learned something. What it had not learned was how to compensate for a monitoring failure it did not know it had. The day began in northern Ohio, in the suburb of Eastlake, northeast of Cleveland, where a generating plant had been running to meet the high electrical demand of a hot August afternoon. Shortly after noon, that plant went offline. A generating unit dropping out of service is a routine event, the kind of single component loss that N1 planning is specifically designed to handle. The surrounding grid was supposed to absorb the loss and redistribute the load across the remaining transmission lines in the region. That is what the system was built to do. At the utility company First Energy, which operated the transmission infrastructure in northern Ohio, an alarm system existed specifically to alert operators when conditions on the grid were moving outside normal parameters. When a line overloaded, when a voltage reading dropped, when the redistribution of load following a generator trip was pushing other components toward their limits. The alarm system was supposed to tell the operators in the control room what was happening and where. The alarm system had a software bug. It had been silently failing for over an hour before the first line went down. The operators at First Energy's control room were watching displays that showed them a version of the grid that no longer existed. Here is what was actually happening on the physical system while the operators watched their incorrect displays. The transmission lines in northern Ohio, rerouting load after the Eastlake plant had dropped offline, were carrying more current than they had been carrying before. High current through a conductor generates heat. Heat causes the conductor to expand. An expanded conductor sags. A sagging conductor drops lower in its span between towers. In the summer, when ambient temperatures are already high, the sag is more pronounced than in winter. This is not a failure of the conductor. It is basic physics understood by every transmission engineer, accounted for in normal operations. Lines are designed with clearance between the conductor and the ground, and between the conductor and any vegetation beneath it, specifically to accommodate this effect. The clearance on this afternoon was not enough. Shortly after 3 p.m., a 345 kilovolt transmission line in the Walton Hills area, southeast of Cleveland, sagged into contact with trees that had grown into its right-of-way. The contact caused a fault. The line's protection system detected the fault and tripped the line automatically, exactly as designed. The load that line had been carrying transferred instantly to the remaining lines in the corridor. Those lines, already stressed, took on more current. They grew warmer. They sagged further. The alarm system, still silent, showed the operators nothing. 3 more high-voltage lines contacted trees and tripped in the following hour. Each trip transferred load to the remaining lines. Each transfer pushed those lines closer to their thermal limits. The operators at First Energy, working from displays that did not reflect what was happening, did not implement the interventions that might have interrupted the sequence. By the time the scope of the problem became visible to grid operators in the wider region, the cascade had already passed the point where local action could contain it. At 4:05 p.m., the cascade went regional. Lines across Ohio, Michigan, Pennsylvania, and New York began tripping in rapid sequence as the redistribution of load overwhelmed their capacity. Generators detecting frequency and voltage instability shut down automatically to protect their equipment, removing generation from the system and deepening the shortfall. The physics were the same as 1965. A grid under stress, a triggering event, a cascade that protective equipment could not stop because each protection trip was itself a new triggering event for the next component in line. By 4:13 p.m., roughly 8 minutes after the cascade went regional, the northeastern grid had fractured. The outage covered parts of Ohio, Michigan, Indiana, Pennsylvania, New York, Vermont, Massachusetts, and Connecticut. It crossed into Ontario. Some 55 million people lost power, 45 million in the United States, and 10 million in Canada. To put that number in scale, it was larger than the entire population of California at the time. Some customers had power restored within hours. Others waited up to 4 days. The economic damage from the outage was estimated at nearly $6 billion. 11 people died in circumstances related to the blackout. The joint U.S.-Canada task force that investigated the event concluded that the causes were not exotic. Poor preparation and planning, monitoring tools that failed without anyone noticing, internal communication failures at First Energy, the mundane accumulation of institutional lapses that allowed overhead lines to sag into trees, and a power plant dropping offline to become the starting point for the largest blackout in North American history. The comparison to 1965 is not comfortable. After 1965, the industry created NERC and the N1 standard specifically to prevent a cascade from a single component failure. The 2003 blackout began with a single component failure, a generator going offline in Ohio. The cascade that followed was not, in its physical mechanics, fundamentally different from what happened at the Sir Adam Beck station 38 years earlier. Load transferred, lines overloaded, protection systems tripped, the cascade propagated. The details were different. The structure was the same. What 2003 demonstrated was something that Section 3 gestured toward. A reliability standard manages cascade risk within the conditions it was designed for. N-1 assumes operators have accurate information and the ability to respond. It assumes monitoring systems work. It assumes the grid is operating within its design envelope. When the monitoring system fails silently, when operators are making decisions based on data that no longer reflects physical reality, the standard's protections do not disappear, but their effectiveness depends on a chain of human and institutional responses that can itself break. The 2003 blackout did not happen because NERC failed. It happened because the system was carrying a heavy load on a hot afternoon, because a generator tripped, because lines sagged into trees, and because the people who might have intervened were watching a screen that was lying to them. Every one of those conditions was individually a known and manageable risk. Together, at the same moment, in the same corridor, they were not. That combination, multiple stresses arriving together in a system with thin margins and imperfect visibility, is not unique to 2003. It is a description of how complex systems fail, and the grid that failed in 2003 was, by every measure of age and capacity, in considerably better condition than the grid operating today. The Texas grid did not fail because of a misprogrammed relay. It did not fail because a line sagged into a tree while an alarm system sat silent. It failed because it encountered conditions it had never been designed to survive, and nearly every component exposed to those conditions behaved accordingly. That distinction matters. The 1965 and 2003 blackouts were cascade failures, sequences of events in which a manageable initial problem became unmanageable through a chain of load transfers and protective trips. The system was operating within its design envelope. It was simply pushed past the margins that existed within that envelope. Texas in February 2021 was something different. It was a system meeting whether it had not been built for, and discovering, across 4 days, what that gap between design assumption and physical reality actually costs. The Texas grid is unusual in the American context. The Electric Reliability Council of Texas, ERCOT, manages a grid that covers most of the state and operates largely in isolation from the eastern and western interconnections. There are limited direct current ties to neighboring grids, but they are thin. Texas cannot draw significant power from neighboring states the way a utility in Ohio can pull from Pennsylvania, or a utility in Nevada can pull from California. This isolation is not an accident. It is the product of decades of political and regulatory decisions that kept the Texas grid free from federal oversight by keeping it free from interstate commerce. The consequence of that freedom in February 2021 was that when the Texas grid ran short of generation, there was no large neighboring system to lean on. Winter Storm Uri arrived in Texas beginning February 10th, 2021. The polar jet stream had dropped unusually far south, pulling Arctic air across a state whose grid infrastructure had been engineered for heat, not cold. Texas summers are brutal and well planned for. The grid has extensive capacity for cooling load. What it lacked was winterization. The insulation, the heat tracing on pipes and equipment, the protective enclosures around sensitive components that allow generating equipment to operate in sustained sub-freezing temperatures. On February 13th, some electricity generators began experiencing outages. On February 14th, as temperatures across the state fell to levels not recorded in decades, the situation accelerated sharply. Demand for electricity in Texas hit 69,692 megawatts on February 14th. That number requires context to land correctly. The previous all-time record for Texas electricity demand was set in January 2018 at approximately 66,400 megawatts. The February 14th reading exceeded that by more than 3,200 megawatts. More critically, it exceeded ERCOT's available generation capacity at that moment by approximately 12,329 megawatts. The grid was being asked to deliver power it did not have. At the same time, generators were failing across the state. Natural gas plants, which supply the largest share of Texas electricity, were losing pressure in pipelines that had frozen, were watching instruments fail in equipment bays that had not been insulated against sustained cold, were tripping offline as components designed to operate in temperatures that Texas winters historically produced encountered temperatures that Texas winters historically had not. Coal plants failed. Some wind turbines, those not equipped for cold weather operation, froze. Nuclear generation was reduced. Every major category of generation contributed to the shortfall. This is the detail that most clearly separates 2021 from the earlier blackouts. It was not one fuel type failing. It was not one region or one corridor. It was the entire generation portfolio encountering the same external condition simultaneously, and that condition being outside the design envelope of most of the equipment running. In the early hours of February 15th, ERCOT ordered rotating blackouts totaling 20,000 megawatts of load shed. The Federal Energy Regulatory Commission later described this as the largest manually controlled load shedding event in U.S. history. To translate that number, 20,000 megawatts is roughly the combined peak electricity consumption of the states of Georgia and Tennessee. It is not a rounding error. It is a significant fraction of a major regional grid deliberately disconnected from power to prevent the alternative, which was uncontrolled total grid collapse. Engineers and grid operators who reviewed the event afterward have said in various formulations that the Texas grid came closer to complete failure than most people understood at the time. A total collapse of ERCOT would not have been a blackout lasting days. It would have been a blackout lasting weeks, possibly longer, while the grid was painstakingly restarted from what engineers call a black start, the process of restoring a grid that has lost all generation and all synchronization, which requires careful sequencing and can take far longer than restoring a partial outage. More than 4.5 million homes and businesses lost power. Many lost it for days. Indoor temperatures in homes across Texas dropped toward freezing as heating systems failed without electricity. Pipes burst. Water systems failed alongside the power grid, leaving 49% of Texans with disrupted water service at some point during the crisis. People burned furniture for warmth. People ran cars in garages for heat and died of carbon monoxide poisoning. The death toll is contested, and the contest itself is a finding. The University of Texas at Austin Energy Institute directly attributed at least 57 deaths to the event across 25 counties. The Texas Comptroller cited at least 210 deaths as storm-related. The R Street Institute cited at least 246. The variation reflects different methodologies for attributing death to an infrastructure failure rather than to its immediate physical cause. Hypothermia, a car running in an enclosed space, a medical device losing power. The true toll is almost certainly higher than any of the lower estimates, and the difficulty of counting it reflects something about how infrastructure failures kill. Not always in ways that show up cleanly in a single cause of death column. Economic damage estimates range from $80 billion to $130 billion in lost gross product per the Federal Reserve Bank of Dallas. Broader analyses accounting for property damage, health costs, and long-term economic disruption put the figure between $200 billion and $300 billion. The UT Austin report on the event found that ERCOT had underestimated peak demand by approximately 14%. The grid was operating from a demand model that did not reflect the conditions on the ground. This is a different version of the monitoring failure that appeared in 2003. In Ohio, operators had incorrect real-time data because the alarm system had stopped working. In Texas, operators had incorrect forecast data because the demand model had not been built to anticipate what a polar vortex intrusion would do to a state that had not experienced those conditions in a generation. What connects 1965, 2003, and 2021 is not the specific mechanism of failure. The relay, the sagging line, the frozen generator. These are different physical events. What connects them is the gap between what the system was designed to handle and what it was actually asked to handle at the moment it failed. In each case, the system encountered conditions at the edge of or outside its design assumptions, and the margins that would have absorbed a smaller stress were not sufficient for the actual one. The conditions the grid will face in the coming decades are not going to move closer to the center of the design envelope. Summers are getting hotter, peak cooling loads are rising, winter storms of the Uri type, driven by polar vortex disruptions, are a documented pattern, not a one-time anomaly. The demand placed on the grid is increasing in volume and in unpredictability. The equipment carrying that demand is older. Reliability standards are written against the historical record. They encode what engineers have seen, what utilities have experienced, what the data shows. They are, by their nature, descriptions of the past. The gap between the past those standards describe and the conditions now arriving is not a gap that a reliability standard closes by itself. Texas was told, after a similar but less severe winter event in 2011, that its generators needed winterization. the recommendations were not mandatory. 10 years later, the same equipment met the same conditions in a more severe form, and the same failures occurred. The bill for that gap was paid in February 2021. The question the grid is still living with is whether the lessons from that payment will be acted on before the next one comes due. A large power transformer was designed to sit in one place, do one job, and last for decades without requiring much attention. That design intent, stable, stationary, long-lived, was appropriate for the grid it was built into. A mid-century transmission system carrying predictable loads in one direction, growing slowly and manageably, did not need its core equipment to be interchangeable or rapidly deployable. It needed equipment that was durable. The transformer delivered on that requirement so reliably for so long that the industry built its planning assumptions around the idea that transformers simply work indefinitely until they don't. The problem with that assumption is now visible in the numbers. And before the numbers, the object itself deserves attention because the supply chain crisis that surrounds it is incomprehensible without first understanding what it is and what it does. A large power transformer is the critical interface between the high voltage transmission system and the lower voltage distribution network that delivers electricity to homes and businesses. Transmission lines carry power at voltages ranging from 115,000 to 765,000 volts. Those voltages are necessary for moving large amounts of power over long distances with acceptable losses. They are also lethal at any proximity and unusable by any standard piece of equipment or appliance. The transformer steps that voltage down in stages from transmission levels to the voltages that substations and eventually homes can use. Without a functioning transformer at each node in that chain, the power moving through the high voltage system above it cannot reach anything below it. The transformer is not one component among many. It is the gate. The physical scale of a large power transformer is not what most people imagine when they picture electrical equipment. A large transmission class transformer can weigh between 100 and 400 tons. The largest units weigh more than some buildings. Moving one requires a specialized heavy-haul railcar, a piece of equipment so rare that utilities sometimes have to wait for one to become available before a transformer can even begin its journey from factory to substation. The route itself requires engineering assessment. Bridges along the way must be rated for the load. Road crossings must be evaluated. Turns must be surveyed for clearance. A transformer does not ship like freight. It ships like a construction project. Once it arrives, installation requires site preparation, specialized crews, and commissioning time before the unit is energized and carrying load. From the moment an order is placed to the moment a transformer is operational in a substation, the timeline under normal conditions was measured in months. Under current conditions, it is measured in years. As of the second quarter of 2025, the lead time for a large power transformer in the United States averaged 128 weeks, according to Wood Mackenzie. That is approximately 2.5 years from order to delivery before installation and commissioning. For generator step-up transformers, the units that connect large power plants to the transmission system, the lead time averaged 144 weeks, nearly 3 years. In 2021, those same lead times were around 50 weeks. The change happened in 4 years. Between 2021 and 2025, lead times roughly tripled. The causes are layered. Electricity consumption in the US rose 7% between 2020 and the mid-2020s, reversing a decade of flat or declining demand and catching manufacturers who had sized their capacity to a different market. The surge of investment in renewable energy generation created enormous demand for generator step-up transformers to connect new solar and wind plants to the grid. The aging of the existing fleet accelerated replacement demand at the same time that new installation demand was climbing. And domestic manufacturing capacity, which had been held deliberately lean through the years of flat demand, could not expand fast enough to absorb the combined load. The import dependency that resulted is significant. In 2025, approximately 80% of US power transformer supply comes from imports. The country that operates the largest and most complex electrical grid in the Western Hemisphere manufactures, domestically, roughly 1 in 5 of the large transformers it installs. The domestic manufacturing base that exists faces its own constraints. Grain-oriented electrical steel, the specialized material used to make transformer cores, has limited domestic production, and the tariff environment of the mid-2020s has added cost and uncertainty to the supply chains that fill that gap with imports. Wood Mackenzie projected a 30% supply deficit for power transformers in 2025. The unit price of a large power transformer has risen 77% since 2019. Some categories of distribution transformers have seen price increases of 95% over the same period. A transformer that cost $400,000 before the shortage can now exceed $600,000 under unfavorable procurement conditions before shipping, before installation, before the specialized labor required to commission it. There is a further complication that sits underneath the price and lead time data, and it is the one that most directly prevents the shortage from being solved the way most industrial shortages are solved. Standardization. There are more than 80,000 different transformer specifications across the US power grid, according to the June 2024 National Infrastructure Advisory Council report to CISA. 80,000. In most industries, a shortage of a critical component is addressed by scaling up production of a standardized product. Factories run more shifts. Automation is deployed, inventory builds, but a transformer is not a standardized product. Each one is specified to the voltage, impedance, cooling requirements, and physical constraints of the exact substation it will serve. The utility that needs a replacement transformer does not order from a catalog. It submits engineering specifications, waits for a manufacturer to schedule its order into a production queue, and waits again while a custom unit is built to those specifications. The 80,000 specification problem is not new. It is the accumulated result of a century of utilities building equipment to their own standards, their own substation geometries, their own voltage levels, with no coordinating requirement for interchangeability. The grid was not built to be modular. Its core equipment was built to be permanent. That design choice, which made perfect sense when permanence was the goal, has become a severe liability in a moment when replacement is urgently needed at scale. The aging of the existing fleet adds pressure to a supply chain already at its limits. 70% of large power transformers in service today are 25 years or older. The National Renewable Energy Laboratory projects that failure rates will accelerate significantly after 2030 as the majority of the fleet crosses further beyond its expected service life. A transformer fleet that has been running reliably for decades is entering the portion of its age curve where reliability can no longer be assumed, and where the number of units requiring replacement in any given year will rise, not because of a single external event, but because of the simple mathematics of age. A transformer ordered today in April 2026 will not be delivered until sometime in late 2028 at the earliest, and will not be operational in a substation until 2029 at the soonest. The demand that transformer will need to serve in 2029 is already being planned by data center developers, electric vehicle charging network operators, and industrial facilities that are making investment decisions right now based on the assumption that the power will be there when they need it. Whether those assumptions are correct depends on decisions being made in transformer factories in the United States, South Korea, and Germany on order books that are already full, against lead times that even the most optimistic industry projections do not expect to return to pre-2021 levels before the end of the decade. ASCE projects that distribution transformer capacity in the United States will need to rise between 160% and 250% by 2050 to meet anticipated demand. The number of distribution transformers in the country may need to triple from today's roughly 60 million units. The manufacturing infrastructure to achieve that does not currently exist. Investments to build it, announced by Hitachi Energy, Siemens Energy, Eaton, and others in 2025, total in the billions of dollars, and will not produce meaningful new domestic capacity until 2027 at the earliest. The transformer was designed to be a long-lived, stable, set and forget piece of infrastructure. For most of the grid's history, it was exactly that. What it has become is a bottleneck at the center of every path forward, replacing aging equipment, connecting new generation, meeting rising demand, hardening the system against the failures documented in 1965, 2003, and 2021. Every one of those goals requires transformers, and the line for transformers is currently about 2.5 years long, with no reliable date for when it gets shorter. For roughly 20 years, the American grid caught a break it did not fully appreciate. Between the mid-2000s and the early 2020s, US electricity consumption was essentially flat. Total demand barely moved from one year to the next. The efficiency gains from LED lighting, more efficient appliances, and improved industrial processes roughly offset the growth in the number of consumers and the spread of air conditioning. Utilities planned around this flatness. Grid operators modeled it. Transmission planners used it as a baseline assumption. The grid was aging, and its margins were thinning, but the load it was carrying was not dramatically increasing. That stability bought time, and the industry used some of that time, though not enough, to address the backlog of aging infrastructure. That era is over. In 2024, US electricity consumption set an all-time record of 4,097 billion kilowatt hours. The Energy Information Administration forecasts that figure will rise to 4,193 billion kilowatt hours in 2025 and 4,283 billion in 2026. The growth is not coming from one direction. It is coming from several simultaneously, and the combined effect is a demand trajectory steeper than anything utility planners were modeling 5 years ago. The largest and fastest growing single source of new demand is data centers. In 2024, US data centers consumed 183 terawatt hours of electricity. To give that number a geography, 183 terawatt hours is roughly equivalent to the entire annual electricity demand of Pakistan, a country of 230 million people. That consumption came from facilities that, in most cases, occupy a few city blocks, run around the clock every day of the year, and are concentrated in a handful of regions: Northern Virginia, Central Texas, the Phoenix metro area, parts of Ohio and Georgia, where land, fiber connections, and power availability have historically coincided. The International Energy Agency projects that US data center electricity consumption will grow by 133% between 2024 and 2030, reaching approximately 426 terawatt hours annually by the end of the decade. The Department of Energy found that data centers consumed 4.4% of US power in 2023, and projects that figure could reach 12% by 2028. These are not fringe estimates from advocacy organizations. They are findings from the federal agencies responsible for modeling the energy system. The driver behind those projections is artificial intelligence, and the scale of what AI infrastructure actually consumes is not well understood outside the industry. A typical AI-focused hyperscale data center, the kind being built by the largest technology companies to train and run large language models and other AI systems, consumes as much electricity annually as approximately 100,000 households. The largest facilities currently under construction are expected to consume 20 times that amount, according to IEA projections. A single building or a single campus, drawing the equivalent power of 2 million homes. That is not a metaphor for large. That is a physical load that requires dedicated transmission, infrastructure, dedicated substation capacity, and in some cases, dedicated generation to serve reliably. The Electric Reliability Council of Texas has fielded requests for 225 gigawatts of new large consumer connections by 2030. To put that in the context of what already exists, the entire installed generation capacity of the US power plant fleet is approximately 1,280 gigawatts. ERCOT alone has received connection requests, totaling nearly 18% of the entire national fleet from large consumers in a single state for delivery within 5 years. Not all of those projects will be built. A significant fraction will be withdrawn, revised, or delayed. But even a fraction of 225 gigawatts represents a demand addition that the Texas grid was not designed to accommodate on its current infrastructure. The consulting firm Grid Strategies, in a November 2025 report, projected that peak electricity demand nationwide could grow by 166 gigawatts by 2030. 166 gigawatts. That is the equivalent of adding 15 New York cities to the grid in 5 years. Not the population of New York City spread across the country, gradually, over a generation, in the way the post-war suburbs spread and the grid expanded to meet them. 15 New York Cities worth of peak demand, arriving in 5 years on infrastructure whose core architecture was designed in the 1960s and whose replacement parts currently have a 2.5-year lead time. The Department of Energy estimated in a July 2024 report that an additional 100 gigawatts of new peak capacity is needed by 2030, with 50 gigawatts of that attributable to data centers alone. A SCE's 2025 infrastructure report card noted that electric vehicles and data centers together will require an additional 35 gigawatts of capacity by 2030, up from 17 gigawatts in 2022. The doubling of that figure in 3 years reflects how rapidly the forecasts have been revised upward, and how little confidence there is that the current projections represent a ceiling rather than a waypoint. The electrification of transportation and heating adds a second, slower moving, but ultimately larger wave behind the data center surge. The Department of Energy projects that meeting full electrification goals across transportation, heating, and industry will require at least a doubling of total US electricity demand by mid-century. Electric vehicles charge at home, overnight, adding load to distribution systems in residential neighborhoods that were designed for the appliance loads of the 1970s. Heat pumps replace gas furnaces and add winter electricity demand to grids that were, in many regions, historically summer peaking. The grid is being asked to serve markets it was not designed for, at a pace set not by engineering timelines, but by technology adoption curves and policy targets. What makes the demand surge particularly difficult to plan for is not its size. It is its pace and its concentration. The post-war build-out that created the grid's current architecture happened over 2 decades, with utilities that had guaranteed customer bases, stable regulatory environments, and the ability to plan long-term capital investment with reasonable confidence. The current demand surge is happening in years, driven by technology, companies whose facility plans change faster than transmission studies can be completed, in regions where the existing grid was not sized for the load, using equipment whose lead times run to years and whose supply chain is already in deficit. The engineers who built the grid in the 1950s and 1960s were building for the America they could see. No utility planner in 2019 had a serious forecast model that included the AI build-out as a material grid planning variable. No transmission study from 2020 was dimensioned around the possibility that a single technology sector would add the equivalent of multiple large cities' worth of load to regional grids within 5 years. The demand now arriving was not visible in the planning horizon when the most recent generation of grid investment decisions was being made. What is visible now is a gap between what is arriving and what the system was built to carry. The grid caught a break for 20 years while demand was flat. That break is over. What comes next is being determined by order books, permitting timelines, transmission study queues, and transformer lead times, all of which are running behind the pace of the load that is already being connected. Somewhere in a regional grid operator's study queue, there is a solar project that has been waiting for 3 years. The developer filed an interconnection request, paid the application fee, submitted the technical specifications of the facility, and entered the study process that every new power plant must complete before it can deliver electricity to the grid. The study process exists for a legitimate reason. Connecting a new source of generation to a transmission system changes the flows on every line in the surrounding network. Some of those lines may not have the capacity to absorb the change, Some substations may require upgrades. Some protection systems may need to be reconfigured. The interconnection study is how the grid operator identifies those requirements and assigns their cost to the project requesting connection. That process, in principle, is engineering due diligence. In practice, it has become a years-long bottleneck through which the country needs to meet. Rising demand must pass before it can maiwanspon operate, and it is backed up in ways that have no near-term resolution. At the end of 2023, Lawrence Berkeley National Laboratory's annual interconnection queue analysis found that approximately 2,600 gigawatts of proposed generation and storage capacity was actively seeking connection to the US grid. 2,600 gigawatts. The entire installed generation capacity of the US power plant fleet, every coal plant, every natural gas plant, every nuclear reactor, every wind farm, every solar array currently operating, totals approximately 1,280 gigawatts. The queue contains more than twice that amount, waiting for a path to the grid. Active capacity in interconnection queues has grown roughly eightfold over the prior decade. In 2013, the queue was a backlog. By 2023, it had become something closer to a structural condition of the energy system, a permanent holding pattern in which the gap between proposed generation and connected generation widens faster than the system can close it. Over 95% of the capacity in the queue is solar, battery storage, and wind. These are not marginal or experimental technologies. They are the resources that utilities, grid planners, and federal agencies have identified as central to meeting the demand surge documented in Section 8, the electrification of transportation and heating, the data center build-out, the industrial load growth that is returning manufacturing to the United States. The generation that the country needs is, in very large measure, already proposed. It is sitting in a queue. The survival rate of queued projects is the data point that reframes the entire picture. Historical analysis by Berkeley Lab found that of all the projects that entered U.S. interconnection queues between 2000 and 2018, approximately 19% reach commercial operation, 1 in 5. The remaining 4 out of 5 were withdrawn, cancelled, or are still waiting. This is not primarily a story about bad projects or speculative developers filing applications they never intended to build. It is a story about a process that the physical system cannot support at the volume being demanded of it. When a study finds that connecting a proposed solar farm requires $200 million in transmission upgrades, and those upgrades require transformers with 128-week lead times, and the developer's financing cannot survive a 5-year timeline to energization, the project withdraws. The grid does not get the generation. The demand it would have served does not go away. More than 70% of interconnection requests are ultimately withdrawn. In 2024, a record 112 gigawatts of solar and storage capacity combined withdrew from US queues, driven by a combination of political uncertainty around clean energy incentives, tariff increases on imported components, rising interconnection upgrade costs, and the simple arithmetic of financing timelines that do not accommodate multi-year study processes followed by multi-year construction and equipment procurement. The withdrawal of 112 gigawatts in a single year is not a signal that the projects were not viable. Many of them were viable under the conditions that existed when they were proposed. What changed were the conditions: the cost of the grid upgrades required for connection, the lead times for the equipment required for those upgrades, the regulatory and policy environment that determines whether the economics of a renewable project close over a 5 to 7 year development timeline. The physical logic beneath the administrative backlog is worth making explicit because it is the part that does not get resolved by reforming the study process. The transmission system was built for a specific generation mix, a specific load profile, and a specific set of power flow directions. Large centralized plants, one-way flows, predictable peaks. The generation now seeking connection is distributed, variable, and in many cases located far from the load centers it is intended to serve. A solar farm in West Texas and a wind project in rural Kansas are not connected to the Dallas or Chicago load centers by transmission infrastructure that was designed to carry power from those locations. The lines that exist were built to serve the generation that existed when they were built. New generation in new locations requires new transmission or significant upgrades to existing transmission before it can deliver power to where it is needed. Building that transmission requires right-of-way acquisition, environmental review, permitting across multiple jurisdictions, and the procurement of transformers, conductors, and substation equipment that are all subject to the same supply chain constraints documented in Section 7. A transmission line from a wind-rich corridor in the Great Plains to a load center in the Midwest can take a decade from initial proposal to energization. The queue does not move faster than the infrastructure that is required to clear it. The compound problem is this. Section 8 established that peak demand is projected to grow by 166 gigawatts by 2030. The generation proposed to meet that demand, and more, is sitting in the interconnection queue, totaling 2,600 gigawatts of proposed capacity. The process of moving projects from the queue to the grid requires transmission upgrades that require transformers with 128-week lead times, transmission line construction with decade-long permitting timelines, and financing structures that cannot survive indefinite study delays. The generation is there in principle. The path from proposed to connected is blocked, not by a single obstacle, but by a compounding sequence of them, each one slow enough to outlast the patience of project developers and the timelines of the investors financing them. FERC has recognized the bottleneck and has required reforms to how grid operators process interconnection requests, moving from a first-come, first-served individual study model to a cluster-based approach that studies groups of projects simultaneously. Regional operators have implemented or proposed additional reforms. In 2024, interconnection agreements reached historic highs, with 75 gigawatts of secured capacity, and 2025 was tracking to match that pace through the middle of the year. These are real improvements. They are improvements to a process whose underlying physical constraint, a transmission system that was not built for the generation mix and load profile now being asked of it, does not change because the study process runs faster. A faster queue that still requires $200 million in transmission upgrades for each major project is a faster queue that still loses 4 projects out of 5. The demand from Section 8 is arriving regardless of whether the queue clears. The generation sitting in the queue is the supply-side response to that demand. between the demand and the supply is a transmission system built in the 1960s, carrying 3 times its designed load with replacement parts on a 2.5-year back order. That is not a Q problem. It is a physics problem with a Q sitting on top of it. The American Society of Civil Engineers knows, to within a few $100 billion, what it would cost to bring US energy infrastructure to a state of good repair and keep it there through 2033. The number is $578 billion. That is the investment gap between what is currently planned and what is needed, calculated against the funding levels established by the Infrastructure Investment and Jobs Act and the Inflation Reduction Act. If those funding levels are not reauthorized when the bills expire, if the nation returns to the infrastructure spending levels that prevailed before 2021, the gap grows to $702 billion by the same date. These are not estimates of what it would cost to build a new grid. They are estimates of what it would cost to maintain and upgrade the one that exists against the demand it is already being asked to serve. The price of adequacy, not transformation. Against that gap, the actual investment picture looks like this. The Infrastructure Investment and Jobs Act committed $73 billion to the energy sector. Investor-owned utilities spent $27.7 billion on transmission infrastructure in 2023, up from roughly $20 billion in 2020, and are projected to spend $32.1 billion in 2026. These are record numbers. Utility transmission investment has been rising consistently for years, driven by the visible pressure of aging equipment, rising demand, and the regulatory requirements that follow major failures. The industry is not standing still. It is running, and the gap is widening anyway. A SCE projects that total U.S. infrastructure investment needs across all 18 categories reach $9.1 trillion. Planned public and private investment totals approximately $5.4 trillion. The overall gap is $3.7 trillion, an increase from the $2.59 trillion gap reported in 2021. The energy sector's grade fell from C- to D+ during the same period in which federal energy investment reached historically high levels. The grade did not fall because spending stopped. It fell because what is being spent is not closing the distance between the condition of the system and the demands being placed on it. This is what engineers sometimes call the recovery gap, and it is the most structurally difficult aspect of the grid's situation. The recovery gap is not a fixed number. It is a relationship between two rates: the rate at which investment and maintenance improve the system, and the rate at which aging, rising demand, and extreme weather degrade it. When the degradation rate exceeds the investment rate, the gap widens even as the spending increases. The gap does not stay fixed while the argument about how to close it continues. It moves. The script has covered a lot of ground since the evening of November 9th, 1965. It is worth pausing here at the end to note something about the relationship between that night and this moment. After the 1965 blackout, the industry understood what had happened. The investigation was thorough. The cause was identified. The institutional response, NERC, the N1 standard, the reliability framework, was serious and significant. It was also reactive. The system failed, and then the system was fixed. To the extent that it was fixed, in response to the failure. The transformer crisis that this script has documented is not a surprise. The ASCE Infrastructure Report Card has been issuing declining grades for the energy sector for years. The DOE assessed transformer and transmission line ages in 2015 and found that 70% of both were already past 25 years. The National Infrastructure Advisory Council published a detailed report on the transformer shortage in June 2024 with specific recommendations and a clear statement of the risk. The NERC Long-Term Reliability Assessment has documented rising peak demand and shrinking reserve margins in successive annual reports. The interconnection queue backlog has been tracked and published by Lawrence Berkeley National Laboratory every year for over a decade. The information exists. It has existed in some form for long enough that the transmission lines installed when the DOE first flagged their age in 2015 are now 10 years older. The gap between knowing and building is not new to this system. It has its own history, and that history is part of the story the grid is living with now. What remains unresolved is not a matter of missing data. It is a matter of timing and consequence. If a large power transformer fails today in a high-load corridor, the utility responsible for replacing it faces a procurement timeline of approximately 128 weeks for a standard unit, assuming one can be ordered immediately and a production slot is available. That is 2.5 years during which the substation that transformer served operates in a degraded configuration with reduced redundancy and thinner margins. During those 2.5 years, the demand in that corridor is not declining. The data centers being built nearby are not slowing their connection timelines to accommodate the replacement schedule. The summer heat domes that push regional grids toward their limits do not pause for transformer procurement. The interconnection queue sits at over 2,600 gigawatts of proposed generation. The reforms being implemented by FERC and regional grid operators are real and are producing measurable improvements in processing speed. What they cannot do is change the physical fact that in many regions, the transmission system does not have the capacity to absorb the generation waiting to connect without substantial infrastructure upgrades, and those upgrades require the same equipment, the same supply chains, and the same permitting timelines that are already stretched. The demand forecasts have been revised upward in each of the last several years. The projections that seemed aggressive in 2022 were revised further in 2023, and again in 2024, and again in 2025. There is no consensus among forecasters that the current projections represent a ceiling. The AI build-out that is driving a significant share of load growth is itself driven by investment and competitive dynamics that do not slow for grid planning cycles. The load is arriving on the timeline of technology adoption, not the timeline of infrastructure construction. None of this means the grid is about to fail. The American power grid is a large, complex, and in many ways, remarkably resilient system. It has been running under stress for decades, absorbing failures that would have seemed catastrophic if they had been predicted in advance, recovering from events that the reliability framework was not designed to prevent. The operators and engineers who run it daily are skilled, and the institutional knowledge embedded in grid operations is deep. What it means is that the grid will continue under stress with margins that vary by region and by season, with equipment that is older than its designers intended, carrying load that its architects did not model, through a demand surge whose endpoint no serious forecaster is currently willing to name. It will continue until something tips. A heat dome settling over a region whose transmission capacity is already at its limit. A major transformer failing in a corridor where the spare inventory has been exhausted by prior events. A winter storm of the Uri type arriving in a part of the country that drew the lesson from Texas that it was a Texas problem. When something tips, the question that matters is how long recovery takes. That question is being answered right now in transformer factories in South Carolina and Virginia that will not be producing at full capacity until 2027 or 2028, in permitting offices where transmission line applications wait years for approval, in utility planning departments trying to build 20-year infrastructure around demand forecasts that change every 12 months, and in the gap between what the system needs and what it is currently receiving, which is wide and which is still growing. The grid built in the 1960s is carrying the weight of a different country. The decisions being made today will determine what happens when that weight, somewhere, finally exceeds what the structure beneath it was built to hold.